Welcome to yet another optimization example. So in this example, a power line is to be run to an offshore facility. The offshore facility is 4 miles down the shore from the power plant and 3 miles out to sea. So just a quick diagram. If here's our shore, so this is land. And then we have our water out here. Basically what we have is we have our power plant. And then we have our offshore facility. And we are being told that sort of the horizontal distance, the distance along the shore, is 4 miles. And then the distance out to sea, just going straight out to sea, is 3 miles. And so what we're wanting to do is we want to run a power line, or the company wants to run a power line, which will run partway along the shore from the power plant and then a straight path through the water at an angle or straight out. And so our power line is going to start, we're going to run along the shore and then cut out through the ocean on a straight path. And then we're told that it costs $50,000 per mile to lay a power line along the shore, and then $80,000 per mile to lay a power line underwater. So I'm going to actually make this slightly larger in one moment. I'm going to draw a larger diagram. It's getting a little cramped. So again, here's our shore. Here's the sea. We have our power plant. And then we have our offshore facility. We know the distance from the power plant to the offshore facility in terms of going along the shore is 4 miles. And then the distance going straight out to sea is 3 miles. And then we're laying our power line so that our power line runs from the power plant along the shore. And then at some point we stop and turn out to sea, and going underwater, we go this way. So what's in purple is our power line. And then we are essentially, we're told that this part, the first part, is $50,000 per mile. And then the second part, the part that's underwater, is $80,000 per mile. And then we are being asked to figure out if we want to spend as little money as possible. So we want to know how far should we travel along the shore? How far should the line run along the shore before it cuts out, in order to minimize the amount of money that we spend, right? So we want to know, we want to minimize money spent. And so we need to know, when we're doing that, we're looking for how long, when does this happen going along the shore? So when should the power line cut to sea? Or where should the power line cut into the sea? So what we'll need to do is we'll need to label our distances. It's completely up to you. We're going to need to know this distance. I'm not going to label them right now. I'm just going to sort of put marks at the ones of interest. So the distance that we travel along the shore is of interest. And then the distance traveled underwater is of interest. Now, the formula, depending on the formula for how we're cutting through water, we're dealing with a right triangle. And so we are likely going to need the Pythagorean theorem for that. And so we have a choice. We could either set my asterisk, that distance along the shore, as our variable, or we could set the remainder as our variable. And that might make our life a little easier, but it's completely up to you. Since we are ultimately being asked, oopsies, I need to erase this in one go. Since we are ultimately being asked to figure out the distance from the power plant till we cut into the water, we can label that as our x. So if we label that as our x, and then this distance as our y, essentially we're trying to minimize the cost for that, right? So the cost, so if we set x equal to the distance along the shore, and if we set y equal to the distance through the water, we can do our restrictions here. I would do the restrictions on x because they're a little more obvious. X has to be somewhere between, either we can cut straight out immediately from the power plant, in which case x would be 0. We could cut through anywhere between 0 and 4 miles, and we also could just go the whole distance along the shore and straight out. So x should probably be between 0 and 4. So we have 0 is less than or equal to x is less than or equal to 4. Now we can go ahead and set our cost equation. So the cost, we have $50,000 per mile. Oh, we should also specify these are in miles. All distances we've been given in this problem are in miles, so we don't have to do any conversions. So the cost, we should have $50,000 per mile along the shore times our x miles along the shore. And then we will have $80,000 per mile through the water times our y miles through the water. And so we need a relationship between x and y. So eliminating all the extra details. Basically what we have is here's our shore. We're looking at a path that runs partway along and then out to sea. And we know that this overall distance is 4 miles. We know this is X and this is Y. So, oh, and then this is 3 miles out, right, dashed line there. So I'm going to also put a dashed line at the bottom. So we essentially have a right triangle with hypotenuse Y. That missing piece, the leg that runs along the shore, is just going to be the remaining 4 minus X miles. So we could figure out Y. So we have that Y should be equal to, or Y squared should be equal to 4 minus X squared plus 3 squared by the Pythagorean theorem. So we have that Y is simply the square root of 4 minus X squared plus 9. So if we go back to our optimization problem, what we have then is our formula for cost. We have C is equal to 50,000 X plus 80,000 times the square root of 4 minus X squared plus 9. Again, we know that X is trapped between 0 and 4. It wouldn't make sense to go past the facility, offshore facility, and then cut back. We'd just be adding extra power line. So from here, we need to take the derivative. So the derivative with respect to X, that first part would just be 50,000. That 80,000 times the square root, again, note that this is the same as 80,000 times, we have 4 minus X squared plus 9, all raised to the 1/2. So if we multiply by a 1/2 out front, we would have 40,000. Then we would have times 4 minus X squared plus 9 raised to the negative 1/2. And then we would have to multiply by 2 times 4 minus X and then times negative 1 to have all of our chain rule. So what we are really looking at is we have C prime of X is equal to 50,000 plus, let's see, we have 80,000 times X minus 4. I multiply the negative inside of the 4 minus X. And then down below, we all have the square root of 4 minus X, the whole thing squared, plus 9. So now we are going to set this equal to 0. So at this point, I should have labeled from here on down, we're doing our optimization. So we want to set this, figure out where this is equal to 0 or undefined. So if we set this equal to 0, we have our 50,000 plus 80,000 times X minus 4 all over the square root of 4 minus X squared plus 9. if we subtract that 50,000 and then multiply by that square root, we'd have first negative 50,000 is equal to 80,000 times x minus 4 all over the square root of 4 minus x squared plus 9. Multiply by that square root, we'd have negative 50,000 times the square root of 4 minus x squared plus 9 is equal to 80,000 times x minus 4. To make my job a little easier, I'm going to go through and just divide by 10,000 on both sides, so I don't have to work with these large numbers. And so this becomes negative 5 times the square root of 4 minus x in parentheses squared plus 9. And on the right side, we just have 8 times x minus 4, or 8x minus 32. 8 times x minus 4. Now, if we want to undo that square root, we should square both sides. So we'll go ahead and square both sides. On the left, negative 5 squared is 25. And then we are just left with that 4 minus x, whole thing squared plus 9. And then on the right, we will have 64 times x minus 4 squared. We could do a variety of manipulation here. I'll go ahead and just multiply things out and rearrange them, but you could notice 4 minus x squared is the same as x minus 4 squared, and we could sort of do a little simplification first if you wanted to, or cancellation first if you wanted to. But if we just multiply things out, this is 25 times, we'd have x squared minus 8x plus 16, and then plus 9. And then on the right, we will have 64 times x squared minus 8x plus 16. So this becomes 16 plus 9 is 25. So we have 25x squared minus 200x plus 25 times 25 is 625. And then on the right, we will have 64x squared minus, let's see, 8 times 64, we should have 272. Sorry, not 272. If we do 8 times 64, we wind up with 512. So we have minus 512 x, and then that would be plus 1024. And then we can go ahead and shift everything over to one side. So moving everything to the right, 64 minus 25, we are looking at 39 x squared. And then negative 512 plus 200 would be negative 312x. And then 1024 minus 625 is 399. So plus 399. This is not getting pleasant numbers. I'm not about to try to factor this. We might as well do our quadratic formula. So we have x equals, for quadratic formula, in this case our a is 39, b is negative 312, and c is 399. The quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we have that x is equal to negative 312 plus or minus the square root of b squared will be negative 312 squared minus 4 times 39 times 399 all over 2 times 39. And I'm going to go ahead and just plug this into my calculator and do the whole thing at once. And we wind up getting, for the x value between 0 and 4, we wind up getting that x is equal to 1.598. Approximately is the one that we care about. So this is where x was equal, or where the derivative was equal to 0. We also need to find where the derivative is undefined. So that means the derivative being undefined, we're just looking at where that denominator would have been 0. So the original derivative was here, right? And so the denominator would have been that square root of 4 minus x squared plus 9. So our derivative is undefined, where the square root of 4 minus x squared plus 9 is equal to 0. And this is never going to happen since we have our 4 minus x in there. So this is never. So what we get from here then is that our points of interest are the endpoints and that 1.598. So 0, 1.598, and 4. So from here then, we will check the cost at each of these values. So we're going to evaluate cost at each point of interest. So again, we'll have our x and our c of x, which once again was 50,000 x plus 80,000 times the square root of 4 minus x squared plus 9. And we are going to evaluate this at x equals 0. That 1.598 we found, I still have the exact number in my calculator, and 4. So if we plug in these values, what we wind up getting is, so we get, when we plug in x equals 0, we get 400,000. When we plug in our x equals 1.598, the more exact value, you get 387,349.94. And we plug in 4, we get 440,000. So again, this is cost we're trying to minimize. We get our minimum cost at that 1.598 and have a minimum cost of $387,349 or $387,349.94. So if we write out our answer, we have the minimum cost is $387,349.94, which occurs if the power line cuts into the water after 1.598 miles along the shore. Just a quick comment. We probably could have made our life slightly easier if we labeled our variables differently. So if instead of labeling X and then Y, if instead we labeled this piece here as X, basically where we do not travel along the shore as X, and then label this as Y, then we travel 4 minus X miles along the shore. This is still 3 miles. And so our cost equation would have been 50,000 times 4 minus X plus 80,000 times the square root of X squared plus 9 would be an alternative equation we could have used for cost. And then of course we would have to finish by finding 4 minus X to figure out when we cut out to C. So this would be an alternative equation for cost if we labeled our variables differently. So presumably, if we solved this problem, we would have gotten that X would be 2.402 approximately. And then we would have had to do 4 minus that to figure out how many miles the line should run along the shore. But there are multiple ways to set up these problems. It's up to you how you want to set it up. Just make sure that ultimately you're answering the original question that was asked.